recording. Okay, so our speaker today is Nicolas Fedorczak. He's a true Normalien. So he did his undergraduate in Economie Supérieure, and afterwards he did his PhD in CA Cadarage, I think with Pascal Monnier-Garbet. And afterwards he left for a postdoc at UCSD with George Tynan and Pat Diamond in the Center for Momentum Transport, right?
Yes.
And so he was part of the dream team of Momentum Transport at that time. And so he's an experimentalist with a passion for theory, or maybe I should say patience for theory. He's one of the rare experimentalists I can discuss and tell the details of my mathematical formulations, and he will listen and ask questions, etc. So he's either very interested in theory or just very kind. He's an expert on edge plasmas with key contributions on scrape-of-layer flows, their effects on turbulence, etc. He's the kind of experimentalist that would come up with a clean, simple formula for a complex phenomenon, maybe hard to justify sometimes, but clearly works. So I'll leave the floor to Nicolas, and he will be the person who will introduce tokamaks and fusion plasmas to the rest of the people. So please.
Okay, thank you, Osgo, for this pleasant introduction. So yes, today I will speak about turbulent transport at the boundaries of tokamaks, and I will try to make a story around the difficult trade-off between confinement and power exhaust in tokamaks. So before starting, I would like to thank all the people being somehow involved in this story. So CA people and Pat Diamond from abroad, yes. So outline is quite simple. I will make brief roundabout toroidal fusion principle to introduce the problem. Then I will speak about interchange turbulence. So describe simple model, comparison with experiment, discuss an important point in tokamaks is interaction of turbulence with sheared flows. And I will finally conclude on confinement and exhaust. Okay, so the objective we have in mind when we do tokamaks is to build a fusion reactor that delivers power. So we want to fuse deuterium, tritium ions to make neutron and helium ion. And to get reasonable reaction rates, we need temperatures above 10 kiloelectron volts. So you have a fully ionized plasma set. And to get a reactor that the job of delivering power, you need a fusion power that exceeds the input power that you deliver to the plasma to sustain this very high temperature or to get to the point. And this basically translates into what we call the triple product, or the Lawson criterion, which is the product of the plasma pressure or density times temperature times the energy confinement time. And this triple product has to be higher than the threatened threshold. So this confinement time, we have to understand it as a time needed for the energy to escape the reactive medium up to the medium boundary, which is the wall, basically, the wall of the reactor. So if you take a ballistic time at 10 kiloelectron volt, it takes about 1 microsecond to travel 1 meter. So this is very, very small confinement time. And to get to that Lawson criterion, you would need huge plasma pressure. And this is done in inertial fusion, and this is absolutely not the target of this talk. Now, another way of solving this problem of huge pressure is to increase the confinement time. So you have to lower the time needed by particles to reach the wall, basically. And because you have charged particles in plasma, you can constrain the trajectories with magnetic field. So transversal to magnetic field, particles will experience Larmor motion of a millimeter to centimeter radius. So in a meter scale reactor, you have good confinement transverse to B, but along field lines, particles are still following a free thermal motion. So the idea of tokamak is to close the magnetic field into a toroidal shape. So you get toroidal closure. So in principle, you close the third dimension in space. But when you do that, in fact, you introduce a gradient of magnetic field in the chamber. The magnetic field is varying like 1 over the major radius. And so particles following a Larmor motion in this varying magnetic field will experience what we call curvature drifts. You have two different contributions for it, but they basically add, and you have a curvature drift that is more or less proportional to the particle energy, inversely proportional to the charge of the particle, and inversely proportional to the product of major radius time magnetic field. And so because of this drift, direction is charge dependent, you get a charge separation in the vertical direction. Electrons move up, for instance, ions move down. So in terms, you create charge separation, so you have vertical electric field. And this vertical electric field translates into radial drift, which is electric field times magnetic field divided by the square of the field amplitude. So this is oriented towards the major radius, along the major radius outward. And this is independent of the charge, so you get the whole plasma moving outward. If you want to a rough ordering of this velocity, if you have only this toroidal magnetic field, would be a large fraction, maybe 10% or around the sound speed of the plasma. So you get, in fact, quite moderate efficiency of this magnetic confinement. And you have, in fact, to compensate this curvature drift. So a simple way to compensate the charge separation is to create a short circuit for the particles to connect the bottom and the top of the plasma. And an easy way to do that is to add a poloidal magnetic field so that particles would follow helical field lines around the plasma, short-circuiting the top and the bottom and cancelling globally the charge separation. So in tokamaks, we do that by inducing or maintaining a plasma current flowing along the toroidal magnetic field that would make this poloidal magnetic field. And other types of devices like stereorators or large helical devices, like in Japan, they use external coils. Well, it makes the shape a bit more complicated, as you see in the picture, but the physics is basically the same. You have, of course, different shaping effects and different forces because in a stellarator, you don't have a plasma current flowing. So it helps in some ways and well, doesn't help in other ways. But basically, what you get from these devices is that with additional power in the range of 1 megawatt per cubic meter of plasma, or even less for a reactor, you reach temperatures of around 10 kiloelectron volts in the plasma center, but you also get strong heat loads on the wall, above or around 10 megawatt per square meter, which is what we are able to extract from current technologies. And you see the tiles you need to protect the reactor from the plasma bombardment. So the reason for that is that when you create helical geometries with poloidal and toroidal magnetic field like this, you have concentric flux surfaces. Plasma is organized like this. And so you have at some point a flux surface that touches the wall. And it is very difficult to imagine a plasma that is perfectly tangential to the reactor wall everywhere, because the plasma moves around, it is unstable, and you have to feedback control it. And so this is basically impossible to keep the plasma in contact with the entire wall section. So you have, in fact, a dedicated interaction area somewhere. And you can then decompose the magnetic equilibrium into confined plasma where field lines turn around forever on the magnetic geometry, and the plasma boundary where field lines intercept the wall. And this is where you get plasma wall interaction as a contact of this boundary plasma with the wall. Okay. And in this open field line specific area, particles flow along field lines up to the wall. And this takes about roughly 1 millisecond. And over this 1 millisecond, particles don't have much time to diffuse across a magnetic field because of confinement is good. And so you have a very narrow plasma extent on plasma facing components. And so you have basically extreme heat loads there. Basically, the rough ordering is that we have about 1 square meter of wall, which is weighted by the plasma. Whereas you have in current experiments, you have about 100 square meter of wall. In ITER or future reactors, you have 1,000 square meter of wall, but you still have only 1 square meter weighted. You still have to exhaust 100 megawatts in a reactor over 1 square meter. You see, you exceed the 10 megawatt per square meter limit that the technology allows. So now, why do we have these very narrow regions? For instance, we can look at what's going on across the plasma radius. So we have power deposited either by fusion or in external systems, and heat is deposited, it hits the plasma, and it can simply, for instance, describe the exhaust of this heat by radial diffusion coefficient, D. So using simple formalism like this, you end up with a confinement time of energy in the plasma, which is basically the square of the minor radius, the distance to diffuse across, divided by the diffusion coefficient. Now in the plasma edge, in contact with the wall, you have temperature in the range of 100 to 10 eV, let's say, so much colder than this 10 kiloelectron volt, but you have much narrower gradients. This is because particles are free to reach the wall. This is the main loss effect that makes this plasma very thin. So we can express this width from the diffusion and this parallel transit time to be the square root of diffusion time, transit time. Okay. So now let's assume that this confinement time and width of the boundary layer are linked by diffusion coefficients that are probably different in amplitude, because in the core and at the edge, you see you have a strong difference of temperature. So probably diffusion coefficients are different by amplitude, but let's assume that they depends with the same sensitivity with control parameters. For instance, plasma current, magnetic field strength. So if you do that, you can reconstruct what would be the fusion efficiency of your reactor, which is basically the fusion power divided by the input power. So you have to be.
I guess we're allowed to interrupt for short questions, right, Mr. Chairman? So yeah, I give you a hard time in San Diego. Why not here too, Nico? I mean, isn't the use of a diffusion coefficient in the scrape-off layer completely ridiculous? You have no separation of scales in either space or time.
Yes, that's true. I mean, we'll see that later.
I mean, this is, of course, it's a bad tradition that has acquired momentum, and it's muddying the waters quite seriously now with current events that we'll hear about from Professor Goldston on Friday.
You will see. I mean, this is just a simple picture of transport. And you will see that this is probably not diffusion, of course, yes. But this is just a simple way to link confinement and in the core and in the scrape-off layer. Okay, so assume they can scale, so D at the edge and in the core can scale with the same sensitivity. So if you do this sensitivity scan, you create this relation between the fusion power divided by input power. So fusion efficiency, you have to be above 1 to get a reactor working. And the peak heat load, which is also an important engineering limit for your reactor, which has to be lower than 10 megawatt per square meters. So if diffusion at the very edge is very small, you will get a very thin plasma load on the wall, and you will get extremely high peak heat loads before getting to the Q above 1 threshold. Now, if D at the edge is larger compared to D in the core, you may have an easy access to a region of operation. So, of course, this is very simplistic, because if you, for instance, want to scale current machines to reactors, it's not only magnetic field and plasma current, it's changing the size, it's also changing, and the power is also changing. So overlapping now experimental points on this might be a bit misleading, but let's see. So these points are synthetic experimental points constructed from scaling laws and pick up random scenarios within experimental correlations. And assuming, of course, current machines don't do DT fusions, they only operate with deuterium. Assume you can mix 50% deuterium tritium, use energy confinement time, scaling laws, you can reconstruct the fusion power and build this Q factor. And same thing for Pickett load. And you have experimental points lying there, making a sort of large cloud of points. Of course, much below Q equal 1. Maybe for jet, you have a few points coming close to 1. But you already see from experiments that you access in a lot of experiments the hard limit of 10 megawatt per square meter. And you can do it in current reactors because tiles are not actively cooled most of the time. And so you can, for a few period of time, put a lot of power on them. Now for either and demo, you see that, of course, you get predicted, let's say, fusion efficiency around 10 or more. But you also have Pickett loads above 100 megawatt per square meter, which is something we have to avoid if you want to operate this reactor. So we need to move away from this to get to the blue area. And the only way we know, for instance, to do it is we have to spread the load to the wall. So to do it, we can maybe play with magnetic geometry, but in fact, we have little margins on it. What we intend to do in a reactor is to collide particles, to radiate, recombine using impurity seeding or as things. We can also add stochastic perturbations to geometrically spread and help collisions and dissipation. But at some point, what we see in experiments that you can reduce drastically the heat load, but at the expense of lowering the confinement time, and so you lower the fusion power. So I think it's something very important for ITER is to know if we will be able, and I guess we will be, but to get to the point where we get heat loads below 10 megawatts per square meter with Q above a few units. So this was the roundabout fusion principle. So we see that from experiments, we have fusion compatible confinement, but we have concentrated and intense plasma wall interaction. So I linked the two with simple diffusion model. Now I will dig into what is transport at the plasma boundary. So the first thing on transport is still linked to curvature. You take here an illustration of the plasma geometry in tokamak with flux of faces as a gray thin curves. And for instance, take an ion sitting there. It will follow the field lines, so follow normally the magnetic flux of faces, but we also have the vertical drift. And so, for instance, an ion moving along the current will go up, and with the vertical drift, will experience a flux of phase, which is a bit, or let's say, a trajectory which is shrinked compared to the ideal magnetic flux of phase. Now, if the particle moves in the other direction, it will experience displacement outward of its ideal trajectories. And the displacement between the two is in the range of the safety factor of so it is the helicity of the magnetic configuration times the Larmor radius and times the sign of this parallel velocity. Now, if you add parallel friction to this, things get a bit interesting because parallel friction is just a way to randomize the parallel velocity. And if you randomize the parallel velocity, you at the same time randomize this radial displacement, and this is radial diffusion. Now you end up with a diffusion coefficient from this that can be expressed as a collision frequency times the Larmor radius squared. So this would be primary diffusion you get simply by displacing particles from one Larmor radius at each collision, plus this curvature drift effect that enhances the diffusion by the square of the cylindrical safety factor. Now, in experiments, this is about 3 to 4, so square it's about 10. So you have an increase of 10 by a factor of 10 of this collisional diffusion. So this is what we call neoclassical diffusion. First, this is a very simplistic picture. You should add mirror effects, electric field effects, and so on. But overall, what you find is that this diffusion is overall quite low. So, in fact, if you look at the 70s, it was the main transport mechanism considered for tokamaks, and it was very optimistic for confinement. But at the same time, it's very pessimistic for pore exhaust, because basically the width of the plasma boundary in contact with the wall would be simply this displacement factor, so cylindrical safety factor times Larmor radius. And so this was already pointed out in the 70s, and for some reason it was forgotten because we discovered turbulence in tokamaks, and then it came up 10 years ago by Goldstone, because experimental points were in fact sort of close or showing the same sensitivity as this. So it showed some interest, and well, we'll see what Rob says on Friday about it. But in fact, in tokamaks, this is not what you see. If you have a fast diagnostic that was probably missing in the 70s, in that case, this is a fast visible imaging of 50 kilohertz frequency. What you see when you look at what's going on in the chamber when you have plasma is, so you see, in fact, turbulence, and it is organized in the form of filaments. I would say filament because any perturbation you create will extend along field line with a free thermal motion. So you get an elongated structure along field line, but quite localized, transverse to the magnetic field in range of, let's say, a centimeter. And this moves radially, exactly, again, due to curvature drift, because the curvature drift picture we have here that we canceled for the main, for the global geometry of the tokamak, we canceled it with plasma current, creating a field line helicity. I mean, this is still occurring on a smaller scale. If you simply take this picture and move it to the smaller scale, locally, these filaments or these perturbations don't have any helicity of the magnetic field associated with them. So there is nothing to avoid this charge separation. And this is basically the ruling transport mechanism.
Sorry, just a clarification, Nico. Is
Yes.
your pretty picture there? Is that L mode or H mode we're looking at?
Oh, this is L mode.
All right. Thank you.
Yes, completely. This is L mode. So you see the dashed line would be the separatrix, and you see like this turbulence crossing separatrix and feeding the plasma boundary from the core.
But that makes a difference on the story, as you well know.
What do you mean from L mode to H mode?
The point is, of course, in that in H mode, you develop very strong shear even in the scrape-off layer, and that may be why the Goldstone formula works.
Exactly, I will come to that. Yes. So let's now have a closer look to this phenomenon of interchange. So to describe this effect, we need some conservation equations. So the first one is conservation of pressure or density, for instance. The model was originally dedicated to isothermal plasma, but didn't change much. So you have time derivative of pressure is balanced basically by parallel losses to the limiter. This is described by loss rates, okay? And you have a source somewhere in your medium. So here we are looking at dynamics across magnetic fields. So we simply get all the parallel dynamics embedded in a simple control parameter, which is a loss rate. Also, the current conservation can be translated into vorticity conservation equations. Vorticity here is the Laplacian of the electric potential. So this is already a rough approximation of the real system, but the time derivative of this vorticity is given by something we call curvature, which is this J parameter, which describes this curvature charge separation effect. So you have a drive for polarization or vorticity, and this is again balanced by parallel losses. In fact, you have parallel currents. Once you have charge separation somewhere along a filament, you have parallel currents appearing. That could be, let's say, slowed down by parallel resistivity, and at some point is slowed down by the sheath resistivity, which is a very thin plasma layer between the actual confined plasma and the wall, or the limiter. So you have this very simplistic system of equation, which is, I think, the minimal set you need to get interchange turbulence. And you see here a picture of the resulting density fluctuation snapshot you get when you solve numerically this system of equation. And you have these nice mushrooms moving outward, which is in fact quite similar to what you get in a Rayleigh-Taylor system, the standard fluid system with gravity, for instance. So, of course, these events are very interesting because you can see them from, let's say, visible imaging, and people very early started to focus on these mushroom events that we call blob. Okay, they have complex shapes, you see, because they have internal dynamics and they interact with other mushrooms or blobs, and so they distort and so on. But still, what we would like to do is to see if we can derive simple ruling laws for these blobs. And quite early, people found that, yes, maybe from this vorticity equation, we can simply order the different terms as sources and sinks. So source would be the vorticity source from curvature, and the sinks would be the parallel dynamics, parallel losses, and the what we call inertia. The fact that to create vortices, you need a density perturbation, but once you have vortices, the density moves away, which basically empties the source of vorticity. So when you do that, you have a very nice expression or simple expression of the blob velocity, function of the amplitude of the blob, density, perturbation, or pressure, the size of the blob, and the control parameters, which are the curvature and the loss rate. So you have basically two asymptotic limits: the sheath limit when curvature simply compensates with parallel currents, and the inertia limit where the curvature source competes with the inertia. Okay, and overall the blob velocity would depend like this, function of the, let's say, wave number of the blob. So you have a maximum velocity somewhere. But one point, I mean, when experimentally I said something I applied, and I was always wondering, okay, but what is the veracity of this? This concerns simple blobs, like nicely shaped density perturbation and vortices. In simulations, this is something much more complicated. Well, so what you can think of experimentally is to try to build average events. So assume a blob, for instance, on a time trace, you have a position somewhere where you measure density in time. You see these peaks, these intermittent peaks on the signal, and assume a blob is simply corresponds to local density maximum on the time trace. And so you can pick up different maximums at around a certain value of the blob amplitude, and you simply conditional average the fluctuations on these specific time events. And what you get from these turbulent maps are indeed these nicely behaving structures. So it shows that, yes, maybe if we do this average, we can get simple objects from complex instantaneous events. Of course, this is a sort of artificial signal projection. You project the signal fluctuations on amplitudes, and these are incomplete because you only keep the local peaks for getting this average done. It's not like a Fourier transform where this is reversible, of course. But still, I think this is an interesting projection of the turbulent map into average objects. And when you do that on simulation, you find an interesting fact is that the average blob velocity you measure in the simulation, because you have the density and the vortices, so you can build the average velocity from this vorticity map built by simulation. In fact, it's very close to what you can get from the model. or should say it differently, the model is close to what you get in the simulation. Basically, it shows that, yes, this approach of blob velocity, balancing different source and sinks terms, may do the job of describing these events statistically or in average. And what you do that when you do that in simulations, you find that the average blob basically is a sit around the the limit between the schists and the inertia behavior. So the sit there where the velocity is in fact maximum. And when you are here, in fact, what you find that the heavier blobs or blobs for which the pressure perturbation is higher, they move the fastest because they have the strongest drive from the pressure of the blob. Well, so the point was in fact to see if we can get this in experiment. So you have here a representation of the Torsupra tokamak, which shows a very simple magnetic geometry, so what we call circular geometry. And at the top there, so crossing the plasma boundary, we had a moving probe. So this is a measurement system with electric connectors that measure basically density and potential. So from this, you can reconstruct the radial drift velocity of the fluctuations, the amplitude, and so you can make this conditional average as is described on this probe and reconstruct average blobs. And you have here an illustration of the comparison between the E cross B velocity or drift velocity of the blobs measured by the probe. You see it spans from about 100 meters per second up to 1,000 meters per second. The vertical axis is a model prediction. And in fact, you have a fairly good agreement statistically over at least one decade. So you have, of course, a finite dispersion because the model is not very accurate. You see already from the simulation, you have some dispersion. But overall, I think it shows that the fluctuations measured in experiment in the plasma boundary is in fact consistent with this interchange picture. But something still I was a bit frustrated with is how you move from individual blobs, like we are describing, to fluxes, because these are fluxes that are interesting to think in terms of confinement or power exhaust. So in principle, if you have a distribution of blobs having certain density and velocity, you need also to know the duty cycle. So which is basically the density of blobs in space or along time, it depends on how you see it. And so you have to know about this intermittency parameter. And of course, you don't have only a single blob population, you have distribution of velocities and amplitude and sizes. So you should know if you want to do that from blob model, you have to think in terms of building a model for amplitude distribution, intermittency distribution. I think this is interesting because this is interesting maybe to think turbulence in terms of population of individual events moving, but bridging the gap between the two, I think this is still an open problem which is not solved yet. So rather than blobs, maybe we can go back to a more standard approach, which is a wave description. So I recall here these two equations for density or pressure. Now I explicited transport terms. And what you can do from this is build, look at the poloidal spectra, because these are the poloidal modes that will create radial fluxes from drift. Okay. What you see here is an illustration of the poloidal spectra of, for instance, radial velocity and density, okay, in simulation. So the black curve would be a time average spectrum, and this is gray curve. So the gray dispersion here is a time dispersion of the spectrum. And I was quite, in fact, interested in the fact that there is no time dynamics in the spectra. Spectra are, in fact, quite constant in time, at least for the amplitudes. I'm not speaking about the phase, but the amplitude of the spectra is quite constant. But something also quite striking is, or I mean, you can expect it from interchange, that the density and velocity fluctuations are in phase over most of the spectrum. So it means that you have the maximum flux allowed by the fluctuations. And now we would like maybe to draw a model for this wave. And to try, we simply overlapped the prediction from the blob model, depending on the wave number. And we were quite astonished to see that this blob model, that is normally meant for describing an isolated blob, it also works for describing the spectrum, more or less. I mean, what you see is that the maximum position of the velocity is correctly predicted. Now you have here an overestimation of the velocity. But of course, you need to apply the blob model, you need a value for the density spectrum as well. And well, again, we tried simple laws, right? And the simple mixing length works quite fine on the spectrum. Maybe not there where you get saturation, but I will come to this later. But the main problem now, when we did this wave description, is that the blob inertia, which is this Reynolds stress, cannot be directly translated into a wave or into spectrum, because this is a nonlinear term. So if you take the velocity and the vorticity at the wave number k, translate into contribution to the wave 2 times k on 0. And so it doesn't work like this. You cannot directly translate the blob model into spectral formalism. So we have to trick it a bit. So what we thought is, okay, there is indeed a dominant mode in the system, somewhere around reference K0 we will define later. And this mode may, in fact, it has a high amplitude, it moves fast in the system. So maybe we could describe its impact on other modes as an effective viscosity. And so the effective viscosity would be simply the potential perturbation associated to this mode K0. And so we make this approximation of translating this Reynolds stress into an effective viscosity. This is for vorticity. Now for density, well, it's still a bit more sort of heuristic in the sense that we introduced also a sort of saturation at mode K0 that we could maybe link to this effective viscosity mode. So we created a modified mixing length, okay, adding here a saturation at K0. And when you do that, in fact, you find that you are quite able to describe quantitatively the spectrum of potential. So you have here, again, the black curve would be the polyidal spectrum of potential from simulation. And the blue one would be this, what we call spectral filament model, where we included this effective viscosity model in it. And we recover the amplitude, the shape, and the position of this K0, maximum velocity wave number. For density, the saturated mixing length or modified mixing length does also a quite good job, even if at low wave number, we are still overestimating the spectrum. But the good thing now with this model is that we can express analytical expression of polyidal spectra for potential and density. And the good point with this model is that you can take away all control parameters into amplitude terms. And you have here a simple normalized spectral shape that is independent of the conditions. So from this, you can build simple expressions of all fluid moments you want: fluctuation level, fluxes, correlation lengths, and so on. So this is what first we tried. We verified against a broad set of simulations where we varied density and, not density, sorry. The transit time, the parallel transit time, and the curvature factor G. And what you find over the simulation is that the model is able to capture the position of the dominant wave number, the amplitude of the potential and density spectra at this wave number, the level of fluctuation that you can measure, and which is more interesting for us is the profile width that we call lambda. So then we were quite happy to see that this simple model can in fact, describe very accurately these 2D simulations. So what about experiments? So again, we focused on a large database from Turbulent using this movable probe, collecting fluctuations from density, potential. We could also measure poroidal correlation lengths. And you have here the illustration of the comparison of the model against experiments. You see, for instance, on the density fluctuation level, well, you have some dispersion. Of course, it's not a 100% match, but still the model is able to capture a range of fluctuation in the range of 20%. This is relatively close to the separatrix for those who know about plasma boundary in tokamaks. For the potential fluctuation level normalized to temperature, yes, this is also quite consistent quantitatively, around 20%. And the same for correlation lengths, poroidal correlation lengths. Statistically, the model does a job, even if there is quite a significant dispersion over the database, but it's something like this. Now, for what interests us in terms of power exhaust, important point that the model is able to capture quantitatively the width of the plasma boundary, quantitatively over a certain range. So that was for Turbulent, and for simple geometries. Of course, reactors do not operate with this simple circular geometry, but still, when you start a plasma in a reactor, during the current ramp up, the plasma will be in contact with the wall with a circular shape. And this is already a concern not to burn the wall already in this phase. So there were a lot of work done to predict the width of the plasma at the boundary in this phase of ITER. And so they ended up building a database with tens of machines, and they make predictions with using scaling laws. And you see here comparison of the prediction from the scaling law in vertical axis for ITER at 3 different currents compared to the model prediction in horizontal axis. And again, you see the model does a job for these ITER predictions within 20%. So I think this is quite remarkable that with this simple turbulent model, we're able now to maybe to predict the width of this Krepphoff layer in these simple plasmas. So this is a point. Now, if you take a real geometry, you will get in ITER, for instance, during the burning conditions, we call this diverted condition, because you have this diverted magnetic shape at the bottom to extract the heat and particles. So this is a strongly shaped plasma compared to the circular geometry. And so again, experimentalists did experimental scaling laws to predict the width of the plasma in ITER in H mode. So I will describe this later, but whatever. The point is they ended up with a very simplistic scaling law with simply the poroidal magnetic field. And you see this lambda varying almost inversely proportional with the poroidal magnetic field of the reactor, of the machine. And for ITER, if you extrapolate, you are here on 1.2. This is above 0.5 millimeter. And this is, of course, very serious. This is very small. So the model, now I'm applying now the model to a synthetic database over these different machines, creating synthetic scenarios within experimental correlations. And I get basically the same trend over existing machines. Now, except that for ITER and demo, I have a factor of 3 to 4 higher predictions at the same field compared to C mode, for instance, which would be a good news. So it shows maybe that the model is still able to capture the right sensitivity of experimental conditions in these strongly shaped conditions. But something I have to mention here is difference of scale. You see that, for instance, in C mode at 1 millimeter, the model predicts about 5 millimeters. So it's off by maybe an order of magnitude. And this is because maybe due to the shaping effect, which was not implemented in the model. So this shaping effect is in fact quite difficult. We thought about it for some time and we didn't find a way to include it in the two control parameters of the model, which is the loss rate and the curvature effect. Something, for instance, I didn't mention in this is that this curvature is oriented along the major radius, and it is dominant there. And if you move away from the from the outer midplane, sorry, this G parameter should decrease in value, because this is basically the scalar product of the major radius direction times the pressure gradient direction. Another important consideration from geometry is that when you have this strongly shaped plasma, you have here an X point, for instance, you see fluctuations having very elongated and distorted shapes. And this is, of course, very difficult to describe with simple models. I mean, we're still thinking about it, and there are probably ways to do that, to implement or to include these complex shapes into simple ruling parameters of the model. But importantly, what you find from 3D simulations performed with Stocham streaks is that no matter the shape of the plasma, circular or diverted, nature of the transport is the same. This is basically interchange. You see here the localization of the flux around the midplane as predicted by this simple geometrical law for curvature. And the same thing for the diverted configuration, except that you see that around the X point, you have strong dissipation, which is maybe the cause of reducing the width of the plasma boundary in diverted configurations. And indeed, from simulations, for otherwise similar control parameters, you find that in circular simulations, you have widths at the boundary, which is about 70 Larmor radii, whereas it falls to 10 Larmor radii in diverted configurations. So it shows a strong impact of the geometry, which is still not understood, but we see that there is this order of magnitude difference simply from interchange, but due to geometry. So we describe a simple model of interchange turbulence. So we describe blobs, which is this basic representation of mushrooms, okay, moving outward. But due to limitation of this blob model, we rather went to wave description, wave model, and this worked pretty well. And in that respect, I was still struggling linking the two. I mean, maybe now you can think that blobs are in fact simple interferences of polyidal waves, so that sometimes you get constructive interference locally and you have a blob appearing out of the picture. But it seems that for me, a wave description is enough to describe the transport at the edge. And we said secondly that the plasma shape is a very important ingredient in setting the absolute amplitude of the transport you get from interchange. So then last ingredient concerning turbulence is the interaction with sheared flows. So spontaneous transport appear at the boundary, as I mentioned earlier. So we have in fact two main confinement modes in tokamaks. We have what we call the low confinement mode, where pressure gradients are, let's say, moderate at around the boundary. And spontaneously, pressure can increase drastically at the edge. And of course, this increase goes up to the core. In fact, you have steep gradients appearing close to the separatrix. And this leads to basically an improvement of the energy confinement time by a factor of 2, which is significant. And this is associated with a strong flow pattern appearing around the boundary. So why we have these flows at the boundary is, first of all, due to the topology of the magnetic configuration. In the confined plasma, if you apply ideal force balance, you find the radial electric field responsible for polyidal flows is scales along the temperature gradient. Now, in the open field line region, things are a bit different because plasma is connected to the wall, and so you have sheath currents allowed through from the plasma to the wall, and this imposes a condition on the plasma potential. And it turns out that radial electric field at the boundary is opposite to the temperature gradient. And so you have naturally this difference, this difference of velocity. And of course, you can reconnect the two with some viscosity. And when you do that, you find that in high confinement, you have a very strong flow inside the separatrix associated with a strong flow in the other direction and outside of the separatrix. And this creates a strong velocity shear. And this is very important because sheared flows, and we will see, can mitigate turbulence. So if you put some vortices in a sheared flow, they will move with the flow, get distorted, and so on. So to describe this simply, you can, for instance, simplify the vorticity conservation equation in 2D. You remove the curvature term, the loss rate, simple vorticity conservation. And let's describe the vorticity as a superposition of a sheared flow. That is, for instance, a parabolic potential, uniform along the poloidal direction, and then a chain of vortices. And this chain has vortices that are localized in the radial direction, so with an envelope, and you have then a Fourier mode. And now you can think that the flow will tilt the eddies, and this tilt is described by this radial wave number kx. And it has to evolve in time if you want to describe the tilt, the change of shape of this chain. And the fact that you use a localized envelope there means that, for instance, a cosine locally, this is in fact describing the mode as a superposition of two waves. And so with a sheared flow, you have a three-wave coupling. So you can go through this simple model, and you have an expression of the Reynolds stress, or for instance, or the drive of the sheared flow in time, which is proportional to the envelope curvature, and of course the tilt of the mode, which is a kx. And this kx evolves in time as a projection of the poloidal wave number by the shear flow, mode tilting. Okay, so if you no, this was a simple description. If you do the simulation of this simple vorticity equation, in time, so you can start, for instance, with a chain of eddies and no sheared flow, but you can start with a tilt, a seed tilt of the eddies, which is enough to start the system. So you have this tilt, it creates a sheared flow. The sheared flow improves the tilt, and you start depleting the chain envelope to feed the shear. And you let it go, and you have this strong depletion of the mode, which is what you expect for turbulent mitigation. But at the same time, know that the envelope has reversed in sign. You take now energy from the flow to give it back to the chain, and you have this sort of Kelvin-Helmholtz instability. And you have now this in time. If you let it evolve, you have this progressive jump between tilting instability, Kelvin-Helmholtz instability. And this is in fact the forward anstrophic cascade along Kx. I mean, this is quite interesting, but at some point there is a missing ingredient here, which is a curvature. Because if you add interchange dynamics, or this curvature polarization term in the system, so you have these blobs, and if you impose a uniform sheared flow in the box of the simulation, you find that basically blobs follow straight trajectories with an average tilt. And it was quite struggling, I mean, to move from this Kelvin or tilt instability to this interchange dynamics with shear that blobs just simply follow an average tilt. And this is in fact because interchange tried to move blobs back to the reference K0, which is along the major radius. And so you have competition between the shear tilt, which is progressive in time, and the interchange recall that forces a blob to come along the major radius. And so you can simply describe it as a recall term in the Kx expression, Kx, so the tilt equation. And we found that a reasonable expression for this interchange recall time is ideal interchange growth, basically. So we checked this against simulations, that the tilt we found in simulation, varying different control parameters, was indeed described by this model. So we were quite happy, and in fact now we had all pieces to build the spectral expression for turbulence mitigation, Reynolds stresses, and so on when you have a sheared flow. So I will not describe these spectra. They're a bit more complicated because you have now a third regime for the spectra. You have still the shear limited regime, the turbulent viscosity regime, and you have now this sheared flow regime that can be very away of this cartoon if the shear is null or weak and comes down and pushes the spectra down. So the effect of the shear flow is to first tilt the mode. So you spread vorticity, so you spread the energy over larger wavelengths, so you have a smaller amplitude, and then you start also to dissipate the amplitude by the Reynolds stress. So different regime of sheared, different shearing regime. But at the end, what you find is that the flux gradient, the flux expression linking the gradient scale length and the shear flow is basically showing that the gradient scale length is inversely proportional to the product of the shearing rate times this interchange time. So it's nothing new. It's fine. But we were able to, from simple models, to embed this in the spectral model. So this I will not go through. We could verify this model against simulation, so it's fine. What you find very importantly now is that the sensitivity of flux, for instance, is the sensitivity of the flux with control parameter is not changed. This is just the amplitude that is impacted by the shear flow, maybe by a factor of 2 to 3, depending on where you are in the shearing regime. And the last point, okay, yes. So the last point on flows is that, as I said, the tilt of the blobs is very important. This is a tilt that drives the Reynolds stress. And now, if you look at the global geometry for tokamak, so you have interchange drive around the midplane, and this creates elongated filaments along the rest of the geometry. But in tokamaks, the magnetic helicity is not uniform in space. It varies spatially. And so you have this magnetic shear that distorts the shape of the structures when you move away from the midplane. And so because you have this interchange drive always there, and you have this drive, so in localized drive in this helical or shear geometry, you create preferential tilts away from the midplane, which are poloidally asymmetric. And so if you want, for instance, to construct a poloidally average model, which is what you need at least for a global picture of what's going on flows or fluxes, you find that if you have an asymmetric plasma shape, you may break, you may break the symmetry of this tilt, and you have a residual tilt appearing over a poloidal average. And this residual tilt of a blob is equivalent to a Reynolds stress. So this can add to, this would be a residual stress exactly for driving flows at the edge. So this was tried in a 1D momentum balance, where we reversed the position of the X point to reverse the sign of the symmetry breaking. And we did that, and we obtained these two different poloidal or radial electric field profiles. And this has to be compared to experimental findings, Torsupra, for instance, or ASDEX, where you find that the change might be qualitatively coherent. This is maybe an effect that takes place in experiment, and that plays on the flow shear and maybe access to H mode. So now I finished on this interaction between shear flow and turbulence. So we showed that the flow shear competes with interchange recall to sustain a tilt of the interchange modes. This leads to turbulence mitigation, Reynolds stress, and again, plasma shape is a key ingredient here. So now I've described this simple picture of interchange transport. Now let's put it back to the perspective of confinement and exhaust. So I recall that for the heat load widths that scale the heat load power, so the heat power loads on the wall. So the model was able to catch the quantitative behavior of experimental findings for circular geometry. So these simple shapes, model is able to get something good. So now I turned the model into an engineering scaling law with cylindrical safety factor, magnetic field, major radius, power crossing separatrix, blah, blah, blah. We saw also from 3D simulations that shaping is important, and this may bring a factor of maybe 7 to this scaling. So let's assume you can add this reduction or mitigation effect from shaping without changing the sensitivity of the model. Now, what you find from experimental scaling in low confinement mode, but shaped plasma like this, that indeed decay lengths are more in the range of a few millimeters than a few tens of millimeters, and this model can predict. But the good point is that the sensitivity from experimental database is very close to what predicts the model. You see on the safety factor, magnetic field, major radius, power, crossing separatrix, we are quite good here. And let's be bold and assume that in experiment, you move from L mode to H mode, you add a factor of 2 decrease of lambda Q. So you can take again this experiment model scaling based and apply these heuristic reductions, still assuming this is interchange. Now for energy confinement, this is a bit bolder, I would say, because this flux model was primarily derived for scrape of layer, assuming you are in contact with the wall. But the parallel damping term we have in the model is in fact quite generic. We could think of different damping terms occurring in the cores that could be plugged in the model. So let's try. You have a flux model. You have a flux expression from the model related to the gradient. And you see here the flux is almost inversely proportional to the square of the gradient decay length. So of course, this is not diffusion, as Pat was mentioning. What you see here, this is not a diffusive expression. This is a pure flux expression from the turbulence. You have here normalized Larmor effect. And you have here that adds to this term again. And so this is sort of close to what we call gyro-Bohm scaling for turbulence. And so assume we could apply this to the core confinement. We, of course, need maybe to adjust the amplitude, because this is very strong as an interchange for the core. But if you do that, you end up with an energy confinement time expressed from the model as an engineering scaling law that is like this. And we compared it to experimental scaling for either, combining different machines. And you have here a comparison of the horizontal axis are the experimental points, and vertical axis is a model prediction for the confinement time. Of course, I adjusted the coefficient in front of the flux to get the right ordering, because this is done for once. And you see that I'm able to catch the right tendency and sensitivity across all different machines, which is quite, maybe expected in a sense that in the core, you have also different interchange mechanisms, but these are still linked to curvature. So maybe here, ingredients are enough. I'm not saying this is correct, but no, you see.
I'm sorry, I have to speak up here. How the hell can you speak of interchange in the core?
Well, you still have
curvature. The average curvature in the core is favorable.
Yes, the same in scrape of layer, but the curvature,
then it's not an interchange.
Okay, might be that. Okay. Might not be interchange, but you still have a curvature, an effective curvature G in the core.
That's not a trivial difference. Why don't you learn about ballooning? It's been a subject of work in this field for 40 years.
Oh, of course, exactly. Yes. Yes, I could speak about ballooning transport. Yes, ballooning modes. Also, okay, yes. No, there is nothing new here, right? I agree, Pat, and this is maybe even too naive. But
the question, look, don't start on the question of is there anything new, then you'll really get me going. But I'm just, if you're going to repeat old stories, you should at least get it right.
Okay.
Well, let him finish, Pat.
I finish. This is the last slide.
Yeah, this is so. Since it's the last slide,
yes. Well, still, the significant difference between the experimental scaling and the model is on the IP and B scaling. Also, aspect ratio, and this is probably pointing that there is a safety factor missing somewhere in the model. maybe on the parallel dissipation rate or something. And this is quite, I think this is also not new, but yes, gyro bomb scaling is not really able to catch exactly all this sensitivity. Now, if we combine these two facts on energy confinement and power loads, okay. Recently, it was showed from experiments on this figure by Brunner, okay, that this plasma boundary width, lambda Q, scale is inversely proportional with average pressure of the plasma, which is equivalent to the energy contained in your plasma, stored in your plasma. You have this strong correlation between the two parameters, which is detrimental for the reactor, of course. And even worse, I mean, it shows that if you go from low confinement mode and high confinement mode, you still follow the same trend, which is basically the same story. You get edge transport barriers that steepen the gradient for the core, which is good, but also steepens the gradient for the edge, for the boundary, which is not favorable for power exhaust. Now, with the model, we basically get the same correlation between the two. But still, you see that ITER and demo, they go away from the model. And this is because the model contains a finite sensitivity with major radius, for instance, that was not contained in Aish scaling, for instance. And this is something we will see. The predictions that does experimental laws like this, we will see what it gives. I'm not saying this is true. I mean, this is just simple model trying to describe experiment with a global picture. So to conclude, so we went through toroidal magnetic confinement. So we have this vertical charge separation occurring. It results in interchange or curvature or ballooning turbulence, as you want. It rules confinement and power exhaust. Maybe, I mean, in broad generic sense. I mean, I'm not saying that we have all. I did not absolutely describe all the detail of core transport, but at least you show that there is a detrimental correlation if you use this interchange description for core and edge, of course. You see, you can have transport barriers developing at the boundary that it is taming turbulence, but because exactly it appears at the boundary between the wall and the confined plasma, it impacts both confinement and exhaust, and we are still screwed with H mode having too thin plasma loads on the wall. So solutions for this currently investigated are adding radiation at the boundary with impurities to radiate power before it reaches the wall, but you end up now diluting the core with impurities, which is not good. Now you could think of expanding the boundary volume as you have here with a very long divertor leg. And of course, along this leg you have more interchange turbulence adding to the spreading of the power. This was proven from experiment, but it goes with the cost of magnetic volume, which is maybe not permitted for a reactor. And then maybe you could think of ways to displace transport barriers away from boundary. This would be a way to gain confinement without getting exhaust issues. And maybe finally, you can also create stochastic layers around the boundary with magnetic fields. This was tested in the 80s, abandoned, or maybe there are ways to do that. So, thank you.
All right, let's thank Nicolas for this valiant effort. And so, questions? I see a hand. Okay, we have Guillaume, go ahead.
Okay, thanks. Well, I have a few questions. So maybe first one, the obvious, the big missing thing in TOCAM 2D and all of those reduced models is sensitivity to threshold and distance to threshold. So first part of the question, can you try to characterize this experimentally, because that would be interesting. And then the corollary is, if you have this sensitivity to threshold, it probably will give you not a single velocity for the blobs, but it will give you a broad distribution of both velocities and the blob sizes and everything. So the fact that your scaling works so well with just one and not a distribution, is it, I don't know, that we're sitting at marginality, or is it a consequence of the way you measure things that only have a small limited window to capture this broad distribution?
I'm not sure. Okay, I agree on the threshold. Okay, there is virtually no threshold imposed in TOCAM 2D. Physics is too simple there to. Yes, frankly, I don't know. I know, for instance, in core physics, you can measure thresholds in terms of fluxes, turbulent fluxes, when you do when you vary local heat deposition, and you can vary the gradients locally. You can exhibit a threshold on turbulent fluxes. At the plasma boundary, I'm not aware of results showing this. And you're so steep anyhow, that I think you are far from thresholds. Now, for blobs, I mean, I agree that the simple blob model tells you something about a single blob dynamics. Now, with a spectral description, we are here describing the entire population of waves. This is okay. You could still say this is a spectra of one blob. Yes, it's fine. This is the spectra of the colloidal correlation lengths you would measure in experiment. But this is still an ensemble of waves. So I'm not sure this answers your question.
Okay, but okay, I guess I have to better understand what you mean by this model. But here you have a spectrum of modes. But what about you can have? Well, what about I guess I'm asking the distribution of size and velocity distribution of blobs and their impact that would have on the decay length.
Well, I mean, this was sort of the strategy we had in mind when we switched from blobs to spectra. Was to say, okay, I don't care about blobs. Blobs might just be sort of interference artifacts or something. We see blobs, so we want to describe blobs, but still you can describe this by waves. And
I agree, but then it's back to the question of threshold, because in TOCAM, then you would need to put by hand a spectrum, a broader spectrum, because you don't have that control to marginality or to whatever that would give you an enhanced spectrum of you call it blobs or waves or whatever. So that is something, because you probably don't have it in TOCAM, that you would need to put by hand. And it would be an interesting thing to actually put it by hand and see how that changes your prediction for the decay length. That's my point.
Yes, okay. Maybe that's something we should discuss with Philip. Maybe Philip tried also some things on TOCAM with killing some modes and see the impact on turbulence and so on.
Okay. Yeah. Well, maybe I'll come back later for the.
Okay.
Thanks.
Okay, Pat, go ahead.
Well, first of many. I mean, putting aside the history of, glad to see you finally learned something about shear flows. Your stay in San Diego accomplished something. I mean, the key point in this was limited to one sentence at the end, right? I mean, the reality is the LaBombard and now Goldston scalings work very well for the current H mode. First of all, H mode is the thing, right? ITER is designed for H mode. We need to be facing H mode. Kikuchi-san is dead right that maybe we should abandon H mode, maybe to negative T. But within, you know, the reality of ITER, we're stuck with it for now. Let's stay in that universe. In H mode, the Goldstone thing works like a charm, and it's easy to see why it works like a charm, because in fact, the shearing effect is so wonderfully stabilizing, right? And you know, you go through the story of the interchange and all, and you have the shearing goes as 1 over the width squared, and the drive goes as 1 over the square root of the width, and the shearing will win for a narrow width, which is what the heuristic drift model gives. And by the way, I mean, we've been through this, and Goldstone left out a few stabilizing effects. It's even worse than he thought, actually. He left out the sheath, among other things. So then you ask, how are you going to get off the hook? Well, one thing you can appeal to is spreading of turbulence, and you can call it spreading, or you could call it an emission of a distribution of blobs. That's a philosophical discourse that we leave to the Normalian philosophers, you know, your colleagues. And then the question is, will that be sufficient to broaden the layer, okay, without degrading confinement too much? And that, in my humble opinion, is the question. Okay, it's easy to see if you dump turbulence into the layer that you will broaden it. But the question is, will you degrade confinement while you do it?
So what is the question?
The question is, what is your views on that? I mean, that to me is what I came to hear about.
But, well, my point is, okay, on Goldstone model, so the neoclassical one, I'm not comfortable with this. I mean, with this neoclassical description of transport at the boundary. Yes, it works. Maybe with factor of 2, you get the right scaling. It's fine. But as I said, with interchange, you get to the right scaling as well.
But what he's saying is there is no interchange, at least originating from linear stability at the boundary. That's the point.
Because shear flow is too strong, you say.
Yes.
Well, I may say maybe it still exists. I mean,
no, but in H mode,
No, but in H mode, the pedestal, you still have turbulence across the pedestal.
Oh, in the pedestal, but then how does it get from the pedestal to the sole? And that is the effect of spreading.
Okay, so
comment on that. I mean, that's the central question in this business. There is some turbulence there, but how does you get it?
Oh, that's no, okay. Yes, that's something I didn't speak about it. I think it maybe relates to the blocking capability of a transport barrier. So you have here a transport barrier that is very thin, localized, and it is maybe thinner than let's say the main wave number of the turbulence. And so you can have developed turbulence maybe inside the shear layer. It spreads, it reaches, and the question is what happens across this transport barrier. So probably you still have a few of this turbulence that spreads if the shear layer is thin enough compared to the turbulence characteristic length.
And the turbulence is strong enough. Yes. It's not strictly a matter of the shear layer, it's the turbulence against the shear layer.
Yes.
The question is, though, for that to be enough to do something interesting for you, is that going to cost you too much in confinement? Do you have an opinion on that?
Well, if you would allow, I have to think about it.
All right, you can think. I'll come back for more questions.
Can I interject? I can maybe ask some question to clarify the things, because I mean, the main discussion is you're putting interchange as an important player, but in fact, the code that you're using doesn't I mean, it uses interchange, but it has the nonlinear term. So you have entropy flux in some sense in this code. So, I mean, interchange may not be the reason of the agreement. It may be the nonlinear physics that you're somehow modeling, because you have the shear flow, you have the nonlinear physics. Interchange is just giving the little thing maybe in the code.
Yes.
I mean, because the code in principle can do spreading as well, because you have entropy flux. That code, I'm sure, is able to spread something. But I mean, that's just the way you're interpreting. I think you're putting too much weight on interchange.
But
and that makes it very weak as an argument.
If I may clarify the clarification, I think it's very important to differentiate, and it's tough, but you know, life's a bitch and then you die. It's tough to differentiate between locally generated turbulence and turbulence that is generated elsewhere and spreading. Because the physics mechanisms in this case, you know, it's like crossing the 38th parallel in Korea, right? The electric field is radically different physics on either side of the line.
Yeah. So do you want to continue, or do we?
Oh, I'll come back for more. I want that we have a real Normalian online. I want to, you know, so.
Okay, so Lothar, go ahead. I see Lothar Schmitz is asking.
Yes, thanks very much. Interesting talk. I had a question more related to a transition that may occur further into the Skraboff layer, and that however influences interactions with the wall and particle transport very profoundly. And that is basically that there must be a transition in collisionality when you go out, in particular in the electron channel, even in reactor relevant regimes where the sheet limit is not relevant anymore, and you become more inertially dominated. And there's also not much E cross B shear anymore. What we see experimentally is that the turbulence becomes increasingly intermittent, and there can be very large density filaments that really are in contact with the wall. Do you see this regime, or in view of what you have said before, which mostly, of course, relates to the very short heat flux with near the last closed flux surface, but do you see this transition further into the Skraboff layer?
You mean in the code? Or
in the
experiment? In the experiment, you mean? Or?
Well, in the experiment, we see the turbulence changes character, right? But do you see it in the code?
Well, in this code, no, because as I said, the parallel dynamics is ruled by a single parameter, which is this parallel loss rate. It was a question we thought about is, well, in that case, I ruled everything with the simple Schiss limit. But you could add in this term an expression for parallel resistivity. For instance, it's true that when you operate a diverter, I need a picture with a diverter now. When you operate a diverter with strong mitigations or high recycling, for instance, you have an enormous increase of the resistivity in this region, which is magnetically connected to the midplane. And this may change completely the dynamics of filaments, yes, because maybe you simply kill parallel current losses, or you at least impact them, and that could, yes, indeed create large blobs that move very fast to the wall, maybe related to what they call density shoulder and so on, yes. But with a code, no, you cannot, in principle, you could create artificially maybe a transition between the two, adding a profile for the parallel loss rate. But I would rather go in the direction of adding more physics in these control parameters to improve what the code can tell. As simple as it is, of course.
Okay, thanks.
Okay, Xavier, go ahead.
Well, I have actually two questions, if the chair allows.
Yeah, sure.
One is actually a follow-up of what you were saying and Pat was mentioning, so I'm sure this one is allowed. it was in the good old time this idea that some turbulence could be generated by the schist itself. Well, that was promoted by our colleagues in Livermore, Schubert and others. I know this was more or less buried because there was this idea that turbulence spreading from the divertor regions to the scrape-off layer would be prevented by the X point. But I've never been fully convinced by that, although historically I was more in the interchange side. But so the idea would be that this time turbulence spreading could come from the divertor region. And also there is this idea that Osgur mentioned that maybe it's all turbulence is not all about interchange. So what is the status so far of this idea? Do you know?
Sorry, I couldn't grab the last sentence. It was
the last sentence is what is the status of this idea that turbulence could come from the divertor region, even the schist itself?
Yes. So you have this. Yes, you have this instability. You could call negative resistivity coming from temperature fluctuations, right? Well, exactly. That's something. In fact, I don't know. I think this is very hard to confirm from experiment. Maybe you would need like specific measurements from this. Maybe that's also something we could look at from 3D simulations, like Solid 3X or Tokamak 3X, because all the physics should be implemented in the code, and you should be able to trigger these schist instabilities from it. Well, and then again, because maybe plasma can be so resistive in the divertor, maybe you can trigger local curvature instabilities that could spread along and impact the midplane confined region. Maybe. But again, the problem is, okay, we need first confirmation, I guess, from 3D modeling experiments. Or no, I cannot say more.
But there is no evidence so far from, for instance, camera measurements that turbulence could spread from the diverter to the scrape-off layer, right?
No, no, because for instance, if you look at images, so fast visible images looking at the divertor, you rather find that the shape of the filaments or fluctuations are such that they are triggered at the midplane, and then they follow sheared flux tubes down to the divertor. So there might be regions where you could have local turbulence in the private flux region, for instance. But yeah, no, I think we don't have so much hints of turbulence generated on the divertor. I mean, of course, you could have, I mean, this was already shown in experiment. Okay, you see this picture is a 3D modeling result of the effective diffusion you get. And what you find is that adding this long diverter leg enhances the global transport, because you have a long leg which is oriented transverse to the radial, to the major radius. So this is perfect for curvature transport or interchange transport. And this enhances in fact, the footprint on the divertor, keeping the same width as the midplane, which was a bit, well, this is in fact, yes, quite intriguing that you can decorrelate the width at the divertor from the width at midplane with this long leg, meaning that at some point you have a parallel flow of a certain width entering the divertor that spreads more with turbulence continuing there. But this is not then impacting back the midplane profile. Okay.
And then I have another very quick question, which is about the mass effect, the isotope effect in our jargon, which is a fashionable subject. I mean, since I guess there is a mass dependence on the width of the
yes, we have a mass dependence.
We lost you there, so we can't hear.
I'm not sure it's so well documented, but for sure. So
yes, I got the point.
Okay.
Okay. So the question is there agreements between the model and the measurement for the mass dependence?
So for instance, you see on this, so this is a comparison of L mode scaling. So it does not contain much of points. It's true. They didn't see any mass dependence. They tried hydrogen and deuterium, and they virtually didn't see any difference. No, the model predicts a weak but finite difference. And well, yes, it's possible that yes, this is ruling out. I'm not sure. I don't know. Frankly, the point is this difference is very small, and experimental conditions are maybe also not helping to distinguish this effect very much.
Okay, Pat has more questions.
Well, thank you very much.
So
sorry. Yeah, maybe I can ask my questions as well before you, if it's fine.
Well, I have a comment on Xavier's point.
Okay, go ahead.
I'll get in right now, and then I'll come back for more after you.
Okay, good.
I've been very interested in the spreading stuff, and then for resolving the soul. And one of the things, well, we thought about, you know, I call it the toilet backing up from below scenario of the sheath thing. The original work on that, which by the way was, as far as I know, was from Ryutov et al. It was Ryutov, Burke, Sidulko, so pretty much made in the USSR, and then it was taken up by Shu. That did not face the effect of the H mode strength shear. That was a rippling mode by any other name, except the resistivity gradient that we would normally take related to the, whatever it is, Spitzer conductivity is now due to the sheath. And that's going to get massacred in a strong shear regime. So, I mean, don't hold your breath is my comment there. And then Oscar, and then I'll come back for more.
Okay, yeah. I mean, predictably, we lost everybody from the geophysical fluid community by now. So I'll ask some questions that they could have asked. Did you try, for example, using potential vorticity in trying to formulate your simple K-spectrum model? Like, because you have an issue with the density and then vorticity, and then vorticity fits in some part and density fits in some other part. Did you try potential vorticity and then potential entropy for?
No.
Would be interesting because it's just a difference between the two equations. It cancels out the parallel term. So, I mean, something interesting maybe to look at.
Okay.
And then the other thing is, can you introduce some antenna in TOCAM 2D for driving some other kind of turbulence? I mean, like, can you make it such that it would be not so stable and like maybe even somewhat damped in most part of the scrape-off layer, and then introduce some antenna to drive turbulence from outside, like in the vorticity field or something?
Well, yes, I think you can play a lot with this simple code. I mean, it's Philip Gendry tried a lot of things.
Yeah, okay.
You can place local damping, see how turbulence turns around and so on. It's in principle, yes, we can do a lot of things.
Okay, all right. Then Pat, go ahead.
All right, so I had two more questions, but yet another pedagogical comment. If you want to read about the effect of curvature in the scrape-off layer, try reading the paper of your fellow Normalian, a real one from 1991, which I had my class read a few weeks ago in UCSD. It'll explain it all to you in nice, pretty pictures. So you don't even have to follow the equations. It works well. It's a good paper. Now to the questions. This story also is ultimately inexorably linked to the H-mode density limit. And it must be because always when you go to the density limit out of H mode, you get a back transition and then you go to Greenwald. And not always to Greenwald, but always the back transition precedes the Greenwald limit. And do you have any comments on that, particularly given that a higher density means a more collisional sheath with the broader layer, which maybe makes the turbulence in the layer go up? And does it invade the core? So does the spreading go, does the old story go, does the tail start wagging the dog?
And you are here describing Goldstone model and what they do with Thomas Reich.
But I mean, this is all these things are linked, right? You can't
yes, of
one
course.
and not the other, right?
Of course, yes. No, I thought about it. I mean, as I said, the model as described here is very simplistic. So parallel dynamics is fake, sort of. Okay, it describes a system. As you say, now if you increase collisionality in the core, in the pedestal, you may have higher. You can start now having an impact on this parallel damping term, and so enhance turbulence, right? So maybe indeed, when you increase the density, you have an increase of collisionality, and then you can enhance turbulence quite strongly at a certain point. No, I still don't see how this can trigger a density limit. I'm still puzzled with this effect. In terms, I mean, for me, if this was a smooth turbulence transition in response of collisionality, you would get something smoother than the abrupt termination of the plasma.
Well, but I mean, the termination isn't so abrupt always, right? As I said, there's a chain of events. I think the critical question is it simply instability in the soul, or is it invasion? You need enough turbulence in the soul to invade the core, again, to punch through the barrier.
Yes.
Again, do you have a comment on that?
But here you postulate that the problem comes from scrape-off layer. True.
Well, the dense says this would say that the H mode density limit problem comes from the scrape-off layer. Not all density limit, not Greenwald. Remember, the H mode density is a two-stepper, right? You always pass through the collapse of the pedestal before you go to Greenwald.
Yes. You lose the H mode. I mean, you go to these grassy elm things and you get. I mean, frankly, if you look at this as a dynamics of the pedestal during this increase of density, it seems to me that the pedestal responds quite continuously to the change of density. So I'm okay. Maybe I didn't look enough into this problem, but didn't jump on me that this was coming from scrape-off layer, really.
So last question, which is kind of a put your money where your mouth is question. Suppose you were given a rather large bank account and you had the freedom to junk eater and start over, which might be a nice event. What kind of thing would you head for? And what mode would you run in? In other words, would you go for H mode as it's designed now, or would you go for one I mode, or my favorite is the wide pedestal H mode? Which one would you pick?
So frankly, I would go L mode. I would go for any confinement modes without an edge transport barrier. Because this
Well,
edge transport.
you're just like Rabu, another no, he's a polytechnician.
True.
Yeah.
But I would try to make something on core transport by some ways. So find a way to control weak shear layers like staircases, things like this. We could control in position and time during a discharge to control confinement, control impurity, migration. The question is how you do that. I mean, internal transport barriers that are triggered by, let's say, reversed magic shear is quite, not sure if this is very stable in time. You see, I think this is quite sensitive. This is a very sensitive scenario. It's not, maybe not foreseen as a main scenario for a reactor. But maybe we are lacking some actuators on transport. I mean, you could think of maybe Bernstein waves to polarize, to create local Reynolds stresses. This is one thing. Not sure it proved entire efficiency there. Something we could think of also maybe is to inject charges in the plasma core. Either deposit charges or create maybe, let's say, a decoupled population of fast particles that could cross plasma and polarize locally, things like this. I would go in this exotic directions.
All right, interesting at least. Good point.
So Guillaume, do you still have a question?
Yeah, I have.
Yeah, go ahead.
Coming back to where you were showing in the limiter you had something for the strip of layer like 70 normal radii and and the diverted one 10 normal radii. I'd just like to have your feeling, because to me it seems a bit comparing apples to oranges in the sense that here you're mixing two effects: the effect in itself, which is interesting, of geometry on the shear layer, the zonal flow strength that you get at the separatrix, and your prediction of the decay length. And those two are, to be fair, I think you would need to operate at constant shear strength and see how diverted, going from diverted to limiter or the inverse, predicts your decay length, and then look at the influence of geometry.
Yes, I totally agree with your point. Yes.
And have you looked at that? Do you have a feel? Because in West you can probably do that in a continuous way, right? So you start limited, and then you progressively build up your diverter.
Well, it's
your X point and measure things.
No, it's not as easy as this in experiment, but it's true that, for instance, all the Torsupra data I've been using for all these measurements made on Torsupra are done with scrape of layers, which are, you see in the scrape of layer widths in the range of 100 ρi. So it's a lot, right, compared to what you get in H mode for lambda Q. So in fact, in this circular plasma experiment, it is true that the shearing rate in the scrape of layer is very weak. But we checked that we were in the weak shear regime to apply these models and so on. Now, it is a good point. I did not check, and we should discuss this with Patrick, is on this TOCAM 3X simulations, in which shear regime were we in the scrape of layer? So maybe it's true that it is already impacted by the shear. So what you see here, this decrease is indeed a result of the shearing rate already in L mode. It's possible, but to me, I think that we are missing ingredients from the geometry. I mean, a clear point is that we don't trigger H mode in circular geometries as we are able to trigger them in diverted geometry.
But you could at least try, I think, to be at constant.
Yes.
Whatever that means, width or strength or etc., and investigate the decay length. I think that would be a much cleaner
Indeed.
exercise.
Indeed.
Okay, thank you very much.
All right, so if there are no other questions, then we thank Nicolas again and terminate the session. See each other on Friday.
Okay, see you. Thank you very much. And thank you, Pat, for your interesting comments.
Actually, I'm going to modify my plan for my talk a bit to reflect this, because I was going to talk about density limits, but we'll bring in a little bit on the soul at the end. I've been working with the student on the spreading issue. So we'll return fire a little bit.
Very good. So, see you on Friday.
Thank you, Nicolas.
Bye.
Thank you, Nicolas. Bye-bye.
Bye.
Bon exposé.